So good afternoon, everyone. I am Ivan Ray P. Almasin.
I am Mark Consuelo.
I am Archie Remirasol.
I am Risijanyo Tapalis.
I am Justin Namunil, and here about to tackle understanding the first law of thermodynamics. So here are the table of contents. So first, we are getting to know what is the first law of thermodynamics. Next is the first law of thermodynamics equation. Third is the first law of thermodynamics limitations, and lastly, the first law of thermodynamics for a closed system.
The first law of thermodynamics, just like mass energy, is always conserved. It can neither be created nor destroyed, but it can be transmitted. For one, so the first is the law of thermodynamics. The first law of thermodynamics is like saying energy is always recycled. It can just appear or disappear. It can only change from one type to another. Like for example, a heat turning into movement or fuel turning into light. The energy inside something like in its moving or interacting molecule is called its internal energy. Wherever a system goes through a unit change due to interaction of heat, work, and internal energy, it is followed by numerous energy transfer and conversions. When a system changes due to heat, work, or internal energy, energy moves around or changes form. However, the total energy remains constant. It doesn't increase or decrease. The second paragraph similarly, if look at the first law of thermodynamics, it affirms that heat is form energy. So, the first law of thermodynamics states that heat is a form of energy and all processes follow the rule that energy is always conserved. This is why it's called the law of conversion of energy. So, what is the first law of thermodynamics? The first law of thermodynamics states that the energy of the universe remains the same. So, the first law of thermodynamics states that the total energy in the universe doesn't change. Energy can remove a system and its surrounding, but it can't be created or destroyed. It explains how it or work affects energy, emphasizing conversion. So the next is the thermodynamic system. In an equilibrium state processes a state variable known as the internal energy or E between the two systems. A system of equilibrium has internal energy when it's transferred between the system. The change of internal energy equals added of the system minus the work it does. So that is the thermodynamic system in the equilibrium state processes in the variable known as internal energy or E.
So to help you understand the meaning of the first law, we can take a common example of a heat engine. In a heat engine, the thermal energy is converted into mechanical energy, and the process is also vice versa. Heat engines are mostly categorized as open systems. The basic working principle of the heat engine is that it makes use of the different relationships between heat, pressure, and volume of working fluid, which is usually a gas. Sometimes phase changes might also occur involving a gas to liquid back to gas. The first law of thermodynamics equation. The equation for the first law of thermodynamics is given as change in internal energy is equal to Q or heat plus W, where triangle NU is the change in the thermal energy of the system. Q is the heat and W is for. So here are some points to remember. For an isolated system, energy always remains constant. Next, internal energy is the point of function and property of system, where internal energy is as extensive property and mass independent, while specific energy is an intensive property or independent or mass. For an ideal gas, the internal energy is a function of temperature only.
So here's some example. So a gas has constant pressure in a system. There's a loss of 45 joules of the heat in the surroundings around the system. So 450 joules of the work is done in the system. So find the system internal energy. So here are the solutions. So change in the internal energy. So Q plus W. So change in the internal energy. So 450 joules plus 450 joules. So change in the internal energy. So equals to 495 joules. So in general, if we want to find the internal energy, so which is denoted by change internal energy, it is important to consider the relationship between the surroundings in the system. So we already know, according to the law, that energy is neither created nor destroyed. Thus, we can tell that anything that is lost by surroundings will be gained by the system. Moreover, the surroundings area will be lost it and carry out some work on the system. So if we look at Q and W, they are positive in the equation, and this is mainly due to the system gaining some heat and work being done on self. The first law of thermodynamics limitation. So here, we will discuss the limitation of the first law of thermodynamics. The law states that whenever a system undergoes any thermodynamic process, it always holds a system energy balance. However, the first law fails to give the visibility of the process or change of the state the system undergoes. So the first law of thermodynamics maintains energy balance in any process but fails to address the visibility or possibility of state changes in the system. The first law of thermodynamics for a closed system. So work done for a closed system, the product of pressure applied in the change, the volume, the occurs due to the applied pressure. So W, so P, change energy to B. So where P is the constant external pressure of the system and change energy, B is the change the volume of the system. So this is specifically called pressure volume work. So the meaning of P is a pressure, and the V is a volume of work. So
So I'm going to discuss the first law of thermodynamics for closed system. The internal energy of a system increases or decreases depending on work interaction that takes place across its boundaries. The internal energy would increase if work is done on the system and decrease if work is done by the system. Any heat interaction that makes takes place in the system with its surrounding also change its internal energy. But since energy remains constant from the first law of thermodynamics, the total change in the internal energy is always zero. If energy is lost by the system, then it's absorbed by the surroundings. If energy is absorbed into a system, then it implies that energy was released by surroundings. So means the internal energy of a system increase or decrease depending on work interaction that takes place across its boundaries. And the internal energy would increase if work is done on the system and decrease if work is done by the system. So we can see in this table the process work done by the system sign conversion for work is negative and work done on the system sign conversion for work is positive. Process heat extract from system sign convention for heat is negative, and heat added to the system sign conversion for heat is positive. So in this next table is the process for closed system.
please do hit the thumbs up button and subscribe for more fun physics content. Let's get into it. Now, it is often said that the first law of thermodynamics is simply a version of the law of conservation of energy. Simply put, conservation of energy tells us that energy cannot be created or destroyed, only transferred from one category to another. So what does this have to do with the first law of thermodynamics? To answer this question, let's first understand what each of the terms in this equation mean. If we imagine that the system that we want to study in this scenario, in order to try and understand this equation, is a gas within a box made up of lots of little gas molecules, then this term in the equation, delta U, refers to the change in the internal energy of our system. Now, internal energy can be thought of as a measure of the state that our system happens to be in as a whole. Even though our system, our gas, is made up of millions of tiny little particles, and we can't track each one of their positions and velocities at each point in time, we can know something about the gas as a whole by knowing its internal energy. Specifically, the internal energy measures how much energy there is within our system, or how much energy it took to make our system from scratch. How much energy would we have to put in to bring together this many particles, with, for example, this particle moving at this speed in this direction at this point in time, and this particle moving with this speed in this direction, and so on and so forth. So that's a brief overview of internal energy. If you want to know more, I'll leave some resources in the description below. But what the first law of thermodynamics does is to look at the change in the internal energy of our system. How does the energy contained within the gas increase or decrease over time? Well, it looks like it does this in one of two ways, as shown by the right-hand side of this equation. The first is heating. When the gas is heated, its internal energy increases. Now, I've already made a detailed video discussing what heat means in a thermodynamic context and how this is different to our day-to-day usage of the word heat. Check it out up here if you haven't seen it already, but in a nutshell, heat refers to the transfer of energy, either to or from our system, that is not directly related to any large-scale or macroscopic forces acting on or exerted by our system. So, for example, if we were to place a flame next to our box, this would transfer energy to our system. This is what we mean by heating, because there are no large-scale forces acting on the box that are resulting in the transfer of energy. And so the two main things to remember about heat as is defined in thermodynamics: firstly, it is a transfer of energy, which is why often it doesn't make sense to say things like heat energy or heat transfer. And secondly, heat is the transfer of energy either to or from our system without any macroscopic or large-scale forces being present. An example of an energy transfer with macroscopic forces present is the following. Let's imagine that instead of one of the walls of our container, we now have a piston. And as the gas particles move around, they exert a force on this piston. That causes the piston to move outward. Well, in this scenario, because the gas molecules are interacting with the piston on a small scale, overall that results on a large scale force that we can actually measure. This is the force that actually causes our piston to move outward. And so this kind of energy transfer, in this case energy transferred from our gas to its surroundings, specifically the piston, is not a form of heating because there's a macroscopic force here. This kind of energy transfer is instead known as work. The energy transferred is equal to the work done by the gas on the piston. And this kind of energy transfer is exactly what the second term in our main equation is referring to. W is defined as the work done by our system, in this case by our gas, onto its surroundings. So overall, the equation relating to the first law of thermodynamics reads the following. The change in the internal energy of our system is equal to any energy it gains as a result of heating minus any energy it loses as a result of the work it does on its surroundings. This is why it's a version of the law of conservation of energy. All we're being told here is that if the internal energy of our system is to change, then this can only happen if there is some form of energy transfer either to our system or from our system. And it's worth clarifying here that we're not saying that only heat can transfer energy to the system because it's positive and work can transfer energy away from the system. No, that's not the case at all, because the value of Q could be negative, for example, if the system is heating its surroundings. And equally, if the surroundings of our system do work on it, then W could be negative as well. Makes sense, right? We do work on the system, we transfer energy to it, and its internal energy increases. And so the point is that our system cannot just magically gain or lose energy. Some form of energy must be transferred to it or from it in order for the internal energy to change. Now, we've already talked a little bit about the sign conventions here. We've defined Q as the energy transferred to our system due to heating, whereas we've defined W as the energy transferred from our system due to work done by the system on its surroundings. Some people find this convention a bit strange and so choose to define the work term the other way around. Specifically, they define it as the work done on our system by the surroundings. And so in both cases now, we note a positive value for the energy transfer if the energy is being transferred to our system, and the value becomes negative if the energy is being transferred away from the system. The only change here, though, is that if we define W as the work done on our system, then we have to put a plus sign in our original equation. At the end of the day, it doesn't really matter which convention we choose, as long as we are consistent with our definitions once we have chosen them. Now, it's important to note that this way of writing the first law, either convention, only works if we're assumed that there is no transfer of matter to or from the system. In other words, we're assuming that no particles of gas, in this particular case, leave our system or enter our system. Because if this were to happen, then there could be some form of energy transfer with these particles, and we would have to include other terms in our first law equation in order for us to account for this type of energy transfer. Only then would our equations still be consistent with the law of conservation of energy. But the point is, I think the most commonly seen equation representing the first law of thermodynamics is this one here, and now we've seen what it actually represents in some basic detail. And with all of that being said, I'm going to finish up here. Thank you so much for watching. If you enjoyed this video, then please do hit the thumbs up button and subscribe for more fun physics content. Hit that bell button if you'd like to be notified when I upload, and please do check out my Patreon page if you'd like to support me on there. Thank you so much for watching, and I will see you very soon.
Experiment time. Materials: insulated container, ice hot water, thermometer. Fill one container with hot water and another with ice. Measure the initial temperature of both. Place the ice into the container of hot water and observe the temperature changes. When the hot water is placed in contact with the ice, heat flows from the hot water to the ice, melting it. The energy transferred from the hot water is converted into latent heat to melt the ice. The temperature of the water decreases as it loses energy, while the temperature of the ice increases as it absorbs heat, showing energy conservation in the process. These experiments show how the total change in internal energy is the result of heat transfer and work done, which are central concepts in the first law of thermodynamics.